Hi, welcome to another lecture on business mathematics. Today we are going to talk about interest rate calculations and application of exponential and logarithmic functions. Let me start by a simple scenario and explain the topic for the discussion today. Suppose you want to start a business, you need $10,000 and you go to your friend, your cousin, to ask him to lend you that money. Well, at that point, you have to give something back. And one way to do that is to give a portion of the company or business you're making to that person, to your cousin or your friend. Standard way to do that is to give stocks of your company in some manner to that person. Alternative approach is to approach a bank and ask for a loan. Once you get a loan, for the privilege of receiving that money, you have to pay certain interest back to the bank. So interest rate calculations comes in there. You borrow money and you have to pay something extra for the privilege of having that money. There are two standard ways of calculating interest. One's called simple interest, which is rarely used, and the other one is compound interest. Simple interest leads to the functions we studied at the beginning of semester. These are linear functions. Compound interest relates to the function we just studied recently, exponential functions, and in particular the number e, and logarithmic functions, and in particular the natural logarithm. Now, let me take you back to the very beginning, the choice between stocks and interest. The two of them couldn't be different more. Let's go take a look at some example of stocks and some examples of kind of things that happens there. So these days computer companies are all in fashion. One of the earlier computer companies was called Commodore. This goes back many years ago, at the time that I was a kid. It was a fashionable name for a certain time, and of course it went bankrupt. So if you had invested your money in Commodore, what would have happened to you in the long run would have been, well, let me show this thing again. At some point, this stock loses all of its value, the company is bankrupt and out of the picture. Opposite to this picture is the picture of another company, very much in vogue these days, is the Nvidia company. Once upon a time, the shares here were like 4 cents, and now it is 140 some dollars. So your money would grow by a factor of 4,000 from 25 years ago up to now. So very different picture. You see the volatility here is story of Commodore, story of Nvidia, very different kind of companies. Commodore was a typewriter company that somehow grew into a computer company. Well, that's a different word. The one that we are going to look at are interest rate calculations. Okay, so we have simple interest. Let's go after that. Suppose you are after that loan of $10,000 from your friend, yeah, and that amount is referred to as the principal. So P is the principal that the money that you borrow or relent at the beginning to another company or a person. Always there is some kind of a interest rate involved. So, for example, these days you hear about the mortgage rates being 6.5% or something like that, and the bank giving you maybe 0.5%. So every establishment has some sort of a rate for the business that they are involved in. And of course, when you make a contract, there is always the issue of for how long you want to borrow your money. So we always have the issue of time involved in our calculations. Well, once you borrow the money, you have to pay back an extra, and that extra is referred to as interest. So I is the interest that you extra money that you pay back for the privilege of having that money in your pocket. When you borrow, you pay something back extra. Or if you lend somebody money, like you give money to a bank, you would expect them to give you an extra at the end of the month because you're lending them money. They can use that money to run a certain business and you want to have a share of it. So when you want to have a share of somebody else's business, your options, basic options are between interest and stocks, one of the two. Okay, let's go back to the simple interest. What was the simple interest? Simple interest amount that you are going to get has all these three items built into it. The principal that you borrow, you lend, rate, and time. So if I borrow 10,000 versus say 20,000, if I double the amount of money that I borrow, well, I expect to pay double the interest. If interest goes up, interest rate goes up, well, I will pay extra interest. So during the inflationary period, R is high. I've seen it going as high as 20%. And during happier periods, R will be low. For example, a few years ago, it was like 3 or 4%. So R is the interest rate that changes. And time, well, when you're borrowing money, are you borrowing it for a month, for a year, for 10 years? Is it a 30-year mortgage or whatever it is? The issue of times always is there. In the simple interest, which makes the calculation so simple, we have the interest is proportional to all these three items. And then we have the accrued amount or the total amount. Okay, so this is a total amount, meaning your original principal, the principal plus the interest. What is the total accrued amount? Well, in this case, our amount is going to be the principal we borrowed. Like if I borrow $10,000 from the bank, I'm expected to pay that $10,000 back plus the interest on it. So that total, I can factor a P out, and then I'll have 1 plus RT for the total or for the accrued amount. So for the linear functions or simple interest, our job's quite straightforward. And this looks like all the linear functions we had at the beginning. So for example, if P and R are fixed quantities and T is the variable, this looks like those mx plus b equation of a line that we had. Well, it's quite rare that people actually calculate this way. Everybody tends toward compound interest. The idea of a compound interest is that the interest, so suppose you take money, put it in your account in the bank. In this case, you are lending the bank some money. At the end of the month, they give you a certain interest. Once that interest is deposited into your account, that's just your money. That's like same as your old money. The old and new are all mixed. There's no separation line between the two of them. And the new interest you earned, that begins to earn interest in the next month. So in the next month, you have interest added on top of the interest you had. So when you have interest on top of the interest, you call it compound interest. Compound interest means earning or paying interest for the purpose of covering the interest from a prior month. And that is where the problem gets a bit more complicated, and exponential functions come in and logarithmic functions come in, depending on what you expect to calculate. So for simple interest, it's just ordinary multiplication and division and so on. But what we are going to get into now is going to be a bit more complicated. So let's get started with that. We are going to start with some hypothetical scenario and then try to build our story and our functions out of that. And I'm going to try to explain where do the formulas themselves come from, as opposed to just saying, well, here's a formula, let's go ahead and learn how to use it. So we are going to dive into this thing at a little bit extra depth to see what is involved. Okay, so and these were the formulas for these are the formulas for simple interest. So interest is PRT and accrued amount is P times quantity 1 plus RT. Now we are going to go to more advanced topic, which is compound interest. So we are going to have additional new terminology. One of them is so-called nominal interest rate, and the other terminology we are going to use is so-called compounding period. So we are going to have R as our nominal interest rate, and then we are going to have and the number of compounding So nominal interest rate simply means that we are going to have multiple numbers coming into play, and each of them are some fashion of some kind of interest rate. There will be a whole list of them. So when you go to a bank during inflation period, you see that they advertise rate and they also advertise yield. So rate and yield are two different things, and you notice the difference when the interest rates are high. Number of compounding periods, well, this is like an accounting system. How many times do you want to compound your money or calculate the interest on interest? So here are some traditional choices. M equal to 1 means yearly. M, for example, equal to 2 means semi-annually. M equal to, next choice, typical choice is 4, which means quarterly. That means every 3 months, so every season, and so on. M equal to 6 means bi-monthly. The one that you encounter most often is 12, which is monthly. Most banking institutions deposit your or give you a balance every month. So you can go to M is equal to 24 to bi-weekly and so on. You have all sorts of choices. If you are really after this thing, you can go 365 for daily. And at the limit of how many times a year you want to compound your money, of course, we have infinitely many, which is referred to as continuous compounding. So we have a whole list of choices. Let me start with some specific numbers, and maybe that helps us understand what's going on. So suppose again we have a principal of $10,000. Say you want to put that much money into a bank account. The nominal interest rate, let's take it a round number that we can play with it easily. No bank these days give you 12%, but just so that our numbers will be easy to work with, I'll pick that number. If you go back 40 years ago, 12% was quite reasonable. So 12%, remember that is 0.12 in decimal numbers. Okay, if we were compounding once a year, what does that mean? It means for you put your money $10,000, you come at the end of the year and the bank says the amount of interest we owe you is the amount of money you put times the rate of interest you're supposed to pay you times the 1 year that you are leaving your money with us, and that becomes 1200. Not bad for at the end of the year. In that you say the total amount is well, 10,000 that you put in the bank plus 1200 that you got as an interest is 11,200. Or you can say 10,000 times 1 plus 0.12 times 1. So that becomes 10,000 times 1.12. When you multiply these two together, you get 11,200. By the way, this is something we call a multiplier. It's an important concept to have in mind when you're compounding. Your money multiplies by some amount. Now, suppose you go to the bank and say, okay, can you give me my interest after 6 months, and I put that interest into the bank. So in this case, you say, well, I calculate my interest is 10,000. I'm putting it for at the rate of 12%, but I'm going to put it for half a year. So here I had 1 whole year. Now I'm going to put it half a year. So that is 6 months, every 6 months or half a year. So my T is half. Okay, well, it stands to reason that now you have $600 interest. Now your money grew by 600, so now you have 10,600. But you promised to leave the money in the account anyway, so you have 10,600. During the second half, you put it there at the, you're always using the same interest, same nominal interest, and that we put it for the remaining half of the year. And now what do we get? So let's go ahead and calculate this thing and see what that is. So I multiply these things and I get $636. Something very important happened. My money grew by the interest from the first 6 months, and then when I calculate the interest on that, I'm getting an extra $36 that were not there in the first 6 months. So now how much money do I have? 10,600, which I had at the beginning, plus 636. I have, when I add them, $11,236. So All the fight is over this extra $36 that you see compared to there. So if I take my money, invest it after 6 months back in the same account, and assuming that the same rate applies, that's why it's called nominal. Assuming same rate still applies, in this scenario, I'm going to have $36 more than that scenario. Now, as the calculations are going to become more involved, let's find a way of simplifying it so that we don't drown under all the numbers and dollars and cents and something. So this is 10,000 times 1 plus this 12%. The bank gives us half of that. Half of that is that number of compounding. And what we are making here is that 10,000 in the first period. We got 6% on that. And in the second period, we got another 6%, but now on top of everything that we already had. So another 1 plus 0.12 over 2. So a more reasonable way of coming up to this number is to take my principal 1 plus the nominal interest rate 12%, 0.12. For each compounding period, the bank is going to give me half of this. But when I leave it in the bank account for the entire year, this multiplication is going to happen twice. So this number is the number of parentheses that I had here, is exactly the same number that's down here. That gives us an idea of what's going to happen in the quarterly. So quarterly, so here I was calculating the accrued amount, the total amount. This is the interest. This is the interest in the first half. This is the interest in the second half. This is the accrued amount. This is after 1 compounding. This is after 2 compounding. And that's what we just call the accrued amount at the very end. In the quarterly scenario of this thing, if I want to calculate the accrued amount, it's actually easier to go and calculate this one. I take my principal, 1 plus the interest rate, whatever interest rate happened to be, divided by the 4 compounding, the 4 seasons that we have. What does that mean? We'll see shortly. So if I want to do this business on a quarterly basis, I say, okay, I'm giving you $10,000 each season, every 3 months. I expect you to take that 12% that you were giving me, divided by 4. So I'll have 3%. But now I'm going to, every season, I bring my money back, put it back into the account, and whatever we saw happen here is going to happen 4 times. So first 3 months, second 3 months, third 3 months, and the last 3 months, I'll have 4 compounding periods. So what is the big deal here? Let's go ahead and calculate this thing, see what happens. So if you go ahead and calculate this thing on your calculator, you get $11,255 and a tiny bit extra 0.881, for example. So what happened? What happened is that look at this extra money. So we went for 1 year from 11,200 every half a year. Semi-annually, we earn $36 extra compared to that. Now we are earning $55 extra compared to that. Because of what? Because we are taking the interest, putting it back into the account, and the interest is earning interest. That's what's called compound interest. So what is the formula for the compound interest? In all the problems we had so far, we had the money left into account for just 1 year. Well, what if I had put the money in the account for 2 years? So if I have 2 years, well, in 2 years, how many compounding periods would I have? For 2 years, it would have been 10,000. The principal is the same. The interest that I get per each compounding period is the same, except that now for 2 periods, I will have 8 compounding to go through. So that gives us the first formula, compounding formula, compound interest formula. So the accrued amount, the total that you're going to have on your account, if you put a principal P and your nominal interest rate is R, you take that R and divide it by how many compoundings that you are going to have per year. And M is going to be number of times you're going to be multiplying that multiplier by itself. And now, as we saw here, if it is 1 year is 4, if it's 2 years is 8. So if you have T number of years, that is how many compoundings that you are going to do. So the cast of characters here are P is the principal, R is the nominal rate. We said nominal as opposed to so-called yield that the banks use. M is number of compounding per year, with the famous cases being what we listed here. You have yearly, semi-annually, quarterly, bi-monthly, monthly, daily, and so on. Whatever you want to use there. And then T is number of years. Now, we said there's an extreme case of continuous compounding. What does that mean? So you can insist on the bank will give you your interest every month, every season, every 6 months, every whatever it is. On an extreme case, if you have a huge amount of money in Wall Street and so on, you're lending money. You could lend money for a day, or you can lend money for an hour and so on. Mathematically speaking, you can take this thing to the limit of calculating your interest at every instant. Every instant means m goes to infinity. And mathematically speaking, something very interesting happens here, which is at the root of our exponential function. If m is taken to its extreme value of being infinity, our formula becomes a very nice, interesting, simple formula. It becomes P exponential of RT. That complicated looking formula collapses to something a lot simpler looking, that exponential of RT, where E is that famous number we talked about, 2.71828, etc. So it's a theorem of calculus that when m goes to infinity, that formula comes very close to this one. Let's go ahead and take a quick look at a demo from Desmos to see how does this look like. Okay, let's take a look at these formulas on Desmos and get a sense of what they mean. So the accrued amount, we said, well, in principle, variable, let's take it to be time. We had equal to principal times 1 plus r over m, close parentheses, to power of mt. Desmos understands that you're trying to calculate a, your main variable is time. It asks you, how about the rest of these things? How about p, r, and m? Do you want to act as a slider? Say yes. So principal is the amount you start with. Let's stick to $1 to keep our numbers small and manageable. Rate of 1 means 100%. That's way out there. So let's make it more reasonable. How do you make it reasonable? You come and click here. It asks you, where do you want this variable to start and end at? Well, our interest rates are always positive, so we better start at 0. Even though in certain countries negative interest rate also works. They charge you for putting money into a bank. Highest interest, well, what's the highest interest you deal with? You see that typically on your credit cards, maybe 25%, 30%, and so on. Let's write 0.25. That's reasonable. M is the number of compoundings that we do. What did we say? The number of compoundings we do once a year. Perhaps we go as far as, say, 12 times a year or something. So we get this picture for what the $1 is going to amount to. Now, we are not going to go negative in time, so I don't need this horizontal axis is my time axis. I don't want to go backward in time, so I slide my picture to the left, maybe down. So what does this graph mean? This, for example, after 5 years, $1 at the rate of 25% is going to amount to almost $3. So if you owe your credit card company $1 and you don't pay it, after 5 years it becomes $3. You realize how dangerous that is. Okay, as a comparison, we said for accrued amount, when you're using compound continuous interest, meaning when m is infinity, let me use the letter b for that. B of t is equal to same principle times exponential of e to the power of rt. You notice that this exponential, you see, it's graphed in black. It's much higher than the red one, even though this red one was at a humongous interest rate of 25%. Continuous is much more than that. Now, at small interest, the difference is less. So for example, if my lower interest, the two graphs come close to each other for the kind of times we are looking at, you see that they are coinciding. But as the rate increases, the gap between these two increase substantially. M was the number of compounding. As we increase m, our accrued amount, the red curve, is going to come close to the black one. Let's see what happens. See, from m equal to 1, I go to 2. That is going to mean semi-annual compounding. So I go to 2, you see, going up. Seasonal meant m equal to 4. I go to seasonal. Here I got 4, you see. I do bi-monthly 6 times a year. I can come closer even. I do monthly. Monthly meant m is equal to 12. You see, by the time I go m to 12, I'm very close to this, but this one always beats all other choices. Compounding continuously, always more than everything else. Now let's go back and do some examples. So suppose say we put $10,000 at a rate of say 8%. Remember, 8% has to be written as 0.08 for 3 years, and compounded every season, let's say. Question is, what is the accrued amount? Again, the formula is P times 1 plus R over M to the power of MT. So it means 10,000 that you're putting down. 1 plus 8%, remember, converted to decimal. You're compounding 4 times a year, so this was a quarterly. In 3 years, how many quarters are in 3 years? 3 times 4. So it becomes 10,000 times 1.02 to the power of 12. Well, we crank our calculator to see what that is. So my calculator, my phone gives me $12,682 and about almost 42 cents. Let's just remind ourselves, if it was simple interest, what would happen? Simple interest would be PRT, well, P times 1 plus RT, let me correct this, 1 plus RT, T, 10,000 that you put down, 1 plus 8%, 3 years, so 10,000 times 1 point, this is 24, so 12,400. Notice simple interest always lower than any kind of compound interest. Now, what about the same thing with continuous compounding? That would be P exponential of RT. So that would be, that's the accrued amount in this case, 10,000 times exponential of this number, 0.08 times 3. So 10,000 exponential of 0.24. What is that? We have to use our calculator. So my calculator shows $12,000 $712 and 49 cents. Notice that this one even beats that one. So as everything else being the same, as you increase M, you are going to have increase in your accrued amount and interest, and Simple interest always lower than all the other options. Continuous compounding always higher than all the other options. Okay, uh, so uh, let's go back and see what happened. We said business environment, you can do sharing either through stocks or through interest rate. Interest rate calculation, I fall in the category of a simple interest that translates into linear functions, or compound interest. We showed that exponential functions come in, and the number e also comes in for the case of continuous compounding. Well, where does logarithm come in? Sometimes in your calculation you try to calculate items that are in the exponent. That is, you're either after r or after t, and in those cases, to capture those numbers from the other information will be like you have the accrued amount, you have the certain target, and you want to find out what t is going to be or what r is going to be. Here is an interesting question. Suppose you want to retire and be a millionaire. Say you are going to retire in 40 years. The question that you have, at what rate should you earn interest so that a certain monthly deposit will help you to make that target? Those kind of questions will bring us to the issue of logarithm and other topics related to more advanced discussions. Okay, until next time, good luck and God bless.